Hello everyone, this is Alas Maori. Okay, since we have been affected by this coronavirus and the classes has been suspended, as you know, so I am thinking of discussing about this Debye model of specific heat. Uh, at least I can send you the screenshot, the discussion over these screenshots, and so let's start, and hopefully you can get everything I would like to convey through this maybe through this video, you can say. So okay, before I start, let me make one point clear. So if you got any of the part within this video where you will not understand, so please you just let me know. You can give me a ring. My number is there on the WhatsApp group of second semester, so I will be able I think I will be able to answer your call anytime you call me. So let's start right away. So when we discuss the instant model of specific heat, we consider the atoms. In fact, the atom to vibrate with only a given frequency. Alright. Whereas in reality, we have already seen that we have got a dispersion relation that looks like omega equal this much, where we can see the modes represented by those dots, the modes in the dispersion relation, and we said that those are the allowed modes that we can have. So now what Debye done, what in this model, Debye model, what the new thing that we did is we consider the dispersion relation, which is omega equals CQ, and this is supposed to be true only in the low K region. As you can see here, the the dotted curves is for this omega equal this much, and this the straight line that you can see is this linear equation that I can have omega equals CQ. So what we do is we only take the region where this linear relation of omega and q are still valid, and we're gonna see that those experimental findings can be explained if we if we start from this dispersion relation that looks like omega equals CQ. Now you must have seen in equation 0.22, if you go to page number 7 on in this text, in this PDF that I've sent you, you'll find that there is a detailed calculations of the density of state as a function of energy, and it goes as energy square. Well, in we already discussed in that here we permit all three modes of vibration to exist. That means you have got, if you consider the x, y, and z axis, the atoms can oscillate in any of those axes. Whereas when we, in the discussion that we had before, we imagine as if the atom are going to oscillate only in the x direction or the longitudinal direction. We completely neglect the transverse direction. But in this case, if you have to derive that density of states, which looks like as quadratic as a function of energy, now you have to consider all those three vibrational modes. That means the vibration along the x, along the y, and along the z axis. And what you're gonna see is you're gonna see the density of state that looks like d omega equal which will be proportional to omega square. Let's just have a look at this equation number 0.22. You can see here d omega equal e square. Please follow this derivation for a better understanding. Now let's go back to where we are. So here we are. So what happened is Now, if you're gonna calculate the total internal energy of the system, you can have, okay, you can you can have the integration from 0 to some maximum energy, okay, to some maximum on energy omega d, which we're gonna discuss later what this omega d that omega d will look like. All right, so if you have to find that energy, okay, you're gonna have the density of states and the energy of each of those levels. All right, so because we are uh, still we are you are still having that vibrational modes where each of the level has energy n, which is n plus half h omega. Now, just like we have done in the instant model of explaining this specific heat, those n, we have taken the average number, and that that expression for n happens because since we are considering the phonons to be, to be behaving like bosons, then this n will be just that distribution function that looks like 1 divided by exponential h omega divided by kbt minus 1. This we know already. And the total internal energy of the system now would just become like E, which is equal to the density of state and the integration over this quantity here. Now, okay, so as I told you that we haven't had any idea about how this omega d is gonna look like, right? So what we're gonna do is, in order to determine this omega d that we call Debye frequency to be precise, what we're gonna do is we're gonna see the total number of modes now. Okay, total number of modes. Remember, previously we were talking about the allowed mode along the x, the y, and the z axis. Now, the total number of vibrational modes, sorry, I should say the total number of modes that you can have. You can see these dots here, which will depend first of all, okay, which will depend first of all on the number of particle ends. Then we have got 3 here because we allow all the 3 modes of vibration to happen, okay. And R here is the number of atom per unit cell. Alright, so this integration is integration from 0 to omega d. I have missed a term here, and it's nothing but density of state. I will correct it and send you the revised note. And this is density of state. We are going to integrate over the density of states. Now, if we do so, okay, with the density of state given from this equation 0.41, you'll find that the Debye frequency will come as this expression. And remember one thing. I should not say remember, but you are going to work out this integration at home. It's a very simple integration, because what we have got is we have got the density of state to be quadratic, okay, with respect to energy omega, and this it will be very simple for you to evaluate omega d from here. You There could be some factor missing out here, but I did it on purpose so that you can check it out, okay. But of course, the factor would be just 2, or the factor 2 that could be in the denominator or in the numerator of these terms under the bracket. Now, if we go back to equation number 0.41, and we know that the specific heat is just the temperature derivative of E, you'll find that C will become like something like this, okay. Now, up to here is fine. So what we have done here is, by considering the dispersion relation to be linear with respect to momentum, well, as remember, we have neglected this part, right? So we are still in the approximation that we have to be in the very low energy, low momentum region. Okay, so what we have is we have got this specific heat to be this equation right here, 0.44. Now another point I would like to now what we do is we are going to look into the two extreme limit, the high and the low temperature limit. So as the experiment says, if you look into page number 8, all right, it says that in the high T region you're gonna see the 3 kb, which is the Dulong-Petit's law, whereas in this low energy region, okay, low temperature region I should say, in this region it's going to behave like Cv, which is equal to T cube, okay, proportional to T cube. Now let's go back here. Now what happened is, let's see whether by using this Debye model of specific heat we can reproduce those what is being observed experimentally. Okay, what is being found experimentally, I mean to say. Now in the high temperature limit, there's a quantity here, h omega divided by kBt, should tend to 0. That is because T would be very high, you can say it's infinity, so that this term would be, you can take it to be 0. Now if that is the case, you know that this exponential of a quantity can be expressed as 1 plus x squared by 2 factorial and so on. So this total term here that you can see, so the 1 will cancel out, leaving you behind only the linear term here, and we are going to neglect the rest of the term because those higher order term will not contribute, because this term itself is close to 0. So you can take, let's say if this term is 0.1, then if you're going to square 0.1, it becomes less than 0.1. And if you're gonna take cube all to the power 4 or to the power 5, it becomes more and more lesser than this linear term here. Alright, so what we're gonna do is we're gonna take this expression here to be of this order. Okay, and now it becomes so easy for us to evaluate this integration, because at the end of the day you're gonna find that the specific heat becomes just 3 kb nr. Now if you take nr on the other side, you get C divided by nr equal 3 kb. That means this is the specific heat capacity per number of particle. Okay, and each of the particle will require this heat in order for it to gain some temperature. Okay, so now what happened is in the low temperature limit, this term it's clear to us that this term would be tending to infinity, very large. All right, and if you look at these terms, so if you, it's like you are considering 1001. So 1000, 1 is nothing compared to the 1000 or the 1 lakh. So we better put this term as, we're gonna neglect minus 1 here and just put only this term. Okay, if you do so, you'll find that the specific heat now becomes this expression here, represent 0.46 equation. Now I'm not going to tell you to solve this integration because it's not going to be easy. Alright, so but by the way, you can do it. There is you can do the integration by parts. Okay, it might lead to some result, but if not, then if one day we can meet in the class, okay, we can do this integration together, but provided we meet again at least in this semester. Okay, and hopefully we'll meet again. And because looking at the trend that we and the trend and updates we are getting day by day, it's going to be worse, but let's hope the good things will happen once and for all. Now this integration here will look like this, okay? Because what happened now is this term itself, remember you have got h bar omega divided by kbt to be high. That means kbt divided by sum by h bar would be a low quantity, right? So we take only the leading term here, and the rest of the term we are going to neglect again. Alright, okay. So if that is so, and this integration here, this integration would be just something that is related to t to the power 4. Now if you are going to differentiate a function that looks like this with respect to temperature, you can find out that this specific heat that we have here would be cubic with respect to temperature. Understand? So this model, okay, this model does agree pretty well with whatever experimental findings that have been established, okay, that that in the low temperature limit it has this sticky behavior, well as in the high temperature limit you have the Dulong's Petit's law. So I think that's all for this part of the video. Next time I think we better put it this way, okay? So I will post this video and maybe through WhatsApp or maybe through the university portal. You're gonna look at this video nicely, okay? Work out these mathematics, and if there is anything, any mathematics that is unclear to you, any physics that is unclear to you, please do let me know. I'm always ready for discussion with you guys. Okay guys, hope I'm making my point clear. So I'll end this video here, and hopefully you can you can get what the message I wanted to tell you through this video. Thanks a lot.